All right, charging a capacitor now through a resistor. This will be a lot shorter than the other one because we already kind of know what's happening. The math is about basically the same, just backwards. Okay, so typically when you set up a circuit to charge a capacitor, it starts off looking like this. So I got my battery here. Oh, use a different color. I got this battery here to like provide the voltage source. It's going to charge everything up. Right now I've got this switch open because I don't want anything to happen yet. So right now nothing's happening. There's nothing happening right now. We're going to have this capacitor and that resistor is on this circuit. So what's important here, this capacitor is initially uncharged. So let me write that. So you say capacitor, that's too small. Capacitor is initially uncharged. So the initial charge on the plate should be 0. Whatever function we come up with for charge on the plates as a function of time needs to start when like at 0 at time 0. That's important, so keep that in mind. Okay, at time 0 we're going to close that switch. Close the switch. Close the switch. Not that switch. Okay, close the switch. Okay. All right. As soon as you close this switch, so you close the switch, this becomes a wire essentially. Okay. Close the switch. I'm not going to leave it like that. Okay. Okay. Immediately it makes a connection and charge will flow and start going through the resistor and putting charge onto the capacitor plates. Okay. Immediately. Charge immediately begins to flow. Charge. Oops. Sorry. Ugh. Okay, I had this working. Why does it refuse? Okay. Sorry, there's like a button on my pen on this one at home that's supposed to let me scroll, but it doesn't. It just scrolls my menu. I thought I fixed it, but I did not. Okay. Charge immediately begins to flow. Okay, on the last video I mentioned what we're going to talk about how to find like I naught and stuff. Basically you need to look out for words like this, immediately. Okay, because that means something. That means immediately, like right when I've closed that switch. Okay, at that moment. Okay, at that exact moment, because the capacitor is uncharged. Okay, there we go. Because this capacitor is uncharged and therefore it doesn't have a delta V across it, it kind of acts like a wire. Okay, electrically speaking, right now, right at time 0, like the delta V across this thing is 0, which electrically speaking, it doesn't exist. Okay, it's like there's just a wire here. Okay, so if you have an uncharged capacitor for a moment, a brief moment in the history of humanity, an infinitesimal second, that thing acts like a wire. Okay, and we can do math pretending that there's no capacitor at all. Okay, at that moment, electrically, the capacitor doesn't even exist. Electrically. I sure hope that's a word. Okay. The capacitor doesn't exist. Okay. And if electrically the capacitor doesn't exist at that very moment, I'm going to have an initial current. So I naught, just like on the last video, going to have an initial current that is whatever the current would have been in this circuit if there was no capacitor. So if there was no capacitor here, I would just have a battery with potential difference delta VT and a resistor of resistance R. And that's it. Okay? So according to Ohm's law, the current in that situation should be just the potential over that resistance R. Okay, so that's going to come back to us later. That's going to help us out. Okay, now let's go back to a little bit later than immediately. Okay, so if you let some time go by, but not a lot, just a little bit of time, okay, at some time t later, okay, at some later time t, okay, at that later time t, I'm going to have current flowing through the resistor. I'm going to have some amount of charge on the plates. Okay. Delta VT hasn't changed. That's still there. Okay. So at this later time t, let's do a loop roll. Okay. Okay, at this later time t, current I will be flowing. And charge Q will be on the plates. Let's do a loop rule. Loop rule. Okay, just like we did on the last video, we're going to do a loop rule. So let's loop it. Remember that switch is closed now. I don't want to draw it closed because then people looking at these notes later will be like, why? What is that? What is happening? Okay, so let's do a nice clockwise loop. And we'll start here right before the battery. So we're going to go over the battery. That's delta V. We're going to go over the resistor in the same direction as current. So we're going to get a negative I times R. And then we're going to get the voltage across this thing. Oh, I guess I should have said that. It's like delta V across the capacitor at that time. Okay. Yeah. Shoot, where's my mouse? Yeah, I should have put that in a block of text, but I think you guys will figure it out. Okay. So, my loop rule will look like, I got my delta V when I cross the battery, then it's going through the resistor, then it's got across the capacitor, and then we're back to where we started, so equals 0. Okay. With the idea that delta V should be the charge on the plates at that moment divided by the capacitance. So now I have delta VT equals, minus IR minus Q over C equals 0. Okay. Alrighty. Now, we're going to do the same thing we did last time. We're going to turn the current into an expression of dq dt. But this time, we are adding charge to the plates. So, as time moves forward, dq dt is a positive number because we are adding charge to the plates. And that matches with the positive current. So, unlike last time we had to put a negative in there. This time, we don't have to do that. Okay, so this time, what color should I do? This time, I equals positive dq dt because the rate of change of Q on the plates is positive with positive current. Because the rate of change of Q on the plates is positive with positive current. Okay, so they just match. We don't have to put a negative in there to make them match. They already do. Okay, so that means that my little equation looks like, instead of I, I'm going to put dq dt. Okay. You might be thinking, hey, but there's a negative there. There was a negative in front of the IR, so I need the negative for that. And then I've got my R minus Q over C equals 0. Okay. And we again have a differential equation. We're going to solve it just like last time, but I think we're going to skip it. Okay. So I'm going to say solve for Q of t, just like we did for a discharging capacitor. Which are further up on these notes. You're solving this differential equation. Yeah, discharging capacitor earlier. I'm not going to redo that math. It's fine. Okay. Okay. And if we do that, oops. If we do that, what we will end up with is this. Okay, we will end up with Q of t equals C delta VT times, or sorry, 1 minus e to the negative t over RC. Okay, if you do that. Furthermore, okay, the charge on the capacitor, there is a maximum. Okay, there's a maximum when everything is done charging. Okay, there's a maximum charge that we're going to call Q final. Okay, so charge on the capacitor, like think about how it's going to charge up. I'm going to go back to the picture a little bit. Okay, like this thing's going to start off with a big current, but as the capacitor charges, more and more delta V is going to be across that thing, which means less delta V across the R. The only way for that to happen is if the current through R is less. Okay, because delta V across the resistor is I times R. Okay, eventually all of the delta V T from the battery will just be across the capacitor. Okay, the more charge there is, the bigger the delta V will be across the capacitor. So eventually there will be no like leftover delta V for the resistor, and then that means the current through the resistor must be 0. When that happens, no more charge will get onto the plates, so there is a limit here. There's a limit to how much charge can go on the plates. Okay, basically the limit is how much charge does it have when delta VC is equal to delta VT, if that makes sense. Okay, so the charge on the capacitor will approach a final value that we're going to call QF. And that QF is the Q we have when, let's see, when the capacitor's potential difference equals the potential difference of the whole, like the battery is just supplying a potential difference across the capacitor to like maintain that charge. That's all it is. So since delta VC equals Q over capacitance, so that means, QF over capacitance equals delta VC. Okay, which means QF equals C delta VT, which is exactly what was happening right here. Okay, C times delta VT. So C delta VT equals final Q, which means I'm going to take my equation here and just replace the C delta VT with QF instead. Okay, so the charge on the plates as a function of time should be some final amount, which is what you would get when you did VT as the just across the capacitor times 1 minus e to the negative t over, hey, there's that time constant again, by the way. Now, we said at the beginning of this that we should, like this function at time 0, I should get no charge on the plates. And now we're looking at infinity, we should get all of the charge on the plates, QF. Okay, so that's what's going on with this 1 minus thing. If you actually graph this thing, the way it looks, I mean, you can see the exponential decay function here, but it's not by itself. It's 1 minus an exponential decay function. That is, like, think of 1 and then subtract exponential decay from it. That's a growth instead. Okay. And it approaches an asymptote at QF. Okay, so hang on. Let me just make sure I get this right. I'm looking at a graph on another thing to make sure I do this right. Okay. All right, so if you graph this thing, this function mathematically does in fact look like, oh, come on, mouse. No, mouse, too far. Okay, fine. Okay, give me a second. I need to make this graph smaller because my stupid thing won't scroll right. I need to see the axes. Okay, so here's Q of t. There is a QF asymptote. Okay, this is a function of time. And it should start at 0 and asymptotically approach QF. Like something like so. That dips down a little bit at the end. It should not. Oh no, I have stroke eraser on. No. Okay. I'm trying. Oh, start at 0. What's wrong with you? Oh, okay, fine. That's supposed to start at 0. I don't know why it's... Okay, well, now it does. Big dot theory. Okay. Note, we do have that tau again. Tau is still RC. If I mark it on this thing, let's see if I can get this right. It would be about... Would it be here? It's again going to be like a 1 over E thing. Let's see. E is about 2.7, so this is going to be a little bit more than 1/3. So that's 1/3. So here-ish. Okay. Tau would be here. Okay, so tau again, remember, time constant. It's a time. It is in seconds. When you are at time RC equal to R times C, you should have 1 over E times the total charge that will be on the plates. So there's that stupid 1 over E thing again. That is something you might be asked to mark on a graph. So just look out. Okay. It is a thing you might be asked to do. We're almost done. Let's look at current. So current is the derivative of this. So we're just going to do that again. Okay. Nothing super fancy. Current. Ooh, did you guys see that? It like flashed weirdly. Okay. Okay. So current is dq dt. No negative this time, just dq dt. Does anybody think saying dq dt sounds cool? Maybe it's just me. Now, I'm actually going to go back to the other version. Instead of QF, I'm going to leave it as the C delta VT because what's going to be nice is something that does something. Okay, so if I do the derivative of the function, I get C delta VT, and then the derivative of 1 minus e to the negative TRC is... bring down the thingy, the one derivatives away, and I just get the minus e thing. So I've got minus, and then the derivative is 1 over blah, 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 e negative t over RC. Okay. Negatives cancel. Boop, boop. Okay. if we look at some things, if I smush them together, I've got C delta V T over RC as my constants, and then my E to the negative T over RC. Boop, boop. Then the capacitance cancels out. And all I'm left with is delta V over R, which, way back up here, we said was, delta V over R was I naught. The initial current. The current that the circuit has when it's kind of ignoring that the capacitor even exists. Okay? I naught equals delta VT over R, which means that I, as a function of time, is initial current, which is delta VT over R, times E to the negative T over RC. Again, that's exactly what it was for a discharging capacitor too. Turns out it's the same time function either way. Current is always some initial current. So whenever a capacitor is involved with a resistor, whether you're charging it or not, or uncharging it, it doesn't matter. The current starts off strong and tapers off to zero asymptotically. Okay. Yeah. Okay, on the next video, we're going to do a summary of all the functions of charging, discharging, and I'm going to go over the words immediately and a long time after.